Welcome, guys, to the second session in the Databaseology lectures on embedded databases. I can't even begin to tell you how excited we are to have that speaker today. Richard Hipp is the creator of SQLite, which, if you don't know this, is the most widely deployed database system in the world. It's on 1 billion Android devices, however many 100 million iPhones are out there. So every single one of you that has a cell phone here is running Richard's code. It's in everything. It's actually going up today too. It was sent out on 200 million AOL installation CDs in the 2000s as well. That's other Richard's claim to fame. I actually looked this up last night. I mean, Richard the success he's had with SQLite is something that I can only dream to have with even the systems that we built here at CMU. Richard code is actually running in space right now. So 2 years ago, they sent up some Android devices that had to be certified by NASA, and it's in the International Space Station right now. So Richard code is running in space. That's the craziest thing you can think about.
I didn't know that.
Yeah. So
without training.
What's that?
And without training.
Yeah, without any training. So again, I'm super excited to have Richard here today, and he's going to tell us about SQLite. So thank you.
Thank you very much, Andy. It's a great pleasure to be here, an honor to be here. Delighted to be with you today. Listen, I've got a bunch of slides. I think that's going to be pretty stuff you're familiar with, but I'm going to click through them pretty quick. So you might want to download a copy of the slides from the URL you see on the screen, because I'm going to be clicking through some things fast, and if maybe you want to go back and look at it later, that's going to be important. And I'm going to probably go too fast for you to take notes.
And the video will be on the website as well.
Okay, yes, video will be on the website as well. So what is SQLite? It's different from most other database engines. It's a library. It's not a system. It's not a process. If you've done a lot of database, if you've worked with any other database, it's probably a system. It's running in the data center somewhere. SQLite's a library that just links into your application. It's a very different thing. It's delivered as a single file of ANSI C code. Now this is a large file, and we don't actually develop by editing that one big file. We have hundreds of files, and then part of our make process kind of concatenates them all together in the right order. But that makes it very easy to deploy. It compiles down to roughly 500 kilobytes. It's very small and compact, small footprint. Low dependencies. It's designed to run on embedded systems. I've got here the minimum set of dependencies. I mean, just standard library things. That's all it is. You don't have to import a bunch of other libraries to get this thing to work. So it can work on embedded systems. A complete database file is stored, or a complete database is stored on disk as a single file, which is an interesting thing. Most other database systems store the content in a directory full of files. And in a lot of systems, that directory is known only to the system administrator. It's some weird place that nobody knows where it is. But with SQLite, the entire database is just an ordinary file. And that means you can take that file and put it on a flash drive or email it to a colleague. It's really easy to move around. It's a full-featured SQL implementation with things like common table expressions, partial indices, full text search, archery indices. It features power-safe serializable transactions. By power-safe, I mean you can be in the middle of a transaction or in the middle of doing a commit, and the system will lose power. And under the assumption that the hardware behaves as advertised, which is not always an accurate assumption, but assuming that hardware does what it's supposed to do, you won't lose any work. Very simple API, easy to program to. It's designed to be able to drop in. It's designed for application developers to be able to take this code, drop it into their application, and have a full-featured database with no other work. And the source code is in the public domain. So you can grab the source code and do whatever you want with it. You can grab a copy of the source code, relabel it AndyDB, and go with it. I mean, that's whatever you want to do. It's called SQLite. People think, oh, it's just a little tiny toy database. It does have its limits, but they're pretty big. We support multiple concurrent writers and one reader, or multiple concurrent readers and one writer all at the same time. Now, that's not huge, but that's usually enough for your embedded device. We take strings and blobs up to 1 gigabyte in size. which is actually more than a lot of large-scale databases will do. A single database can be up to 140 terabytes. We've never actually tested that limit because we've never actually come up with a file system that could give us a 140 terabyte file. But that's the theoretical limit. 64-way joins, 2,000 columns per table. There aren't any real arbitrary limits other than these. It's actually a full-featured database engine.
So what is the forcing function for 140 terabytes? I mean, what limits it?
The limiting factor on the size of the database file, 140 terabytes, is that we use a 32-bit integer to count the pages. Actually, it's a signed integer, so we have to leave the top bit off. And so we have 31 bits, and the maximum page size is 64K. So you do the math. So how did this get started? This was, I'm not, I didn't start out as a database person. I was doing some application development, solving some hard problems, and I was doing these client programs that were doing a really interesting theoretical calculation, but I had to get my data from a database engine. And the client that I was working for provided the database engine, and it was Informix. And hey, it worked great when it worked. But sometimes they would power cycle the database engine, or power cycle the machine, and the database engine wouldn't come back up. And when that would happen, that would mean that my application couldn't do its job because it couldn't read the data, because it had to talk to the database engine. And so my application would bring up that dialog box. And that's what an error dialog box actually looked like in the late 1990s. That's an actual screenshot. They look better now, don't they? Yeah, a little bit grainy. Yeah, yeah, but back in 1998, we thought this was so cool. This was so state of the art. Do you remember that? So I had this idea. Well, look, this particular application, it's not doing a lot of heavy transaction stuff. In fact, it's read only, and it's not doing any elaborate joins or queries. Why can't I just read this data directly from the disk? Why do I need this server sitting in between me and my data, which is just another potential point of failure? So after that project was finished, I had a couple months off, and I wrote SQLite. And that started in 2000. In May of 2000 was first code, and the first release was a few months later. So that's how it got started, and that sort of shows you the motivation behind it. So it's a little bit different from what you're kind of used to seeing. It has different use cases. SQLite is not trying to replace all these other databases that you're more familiar with. SQLite ends up being very useful in embedded devices and the Internet of Things. It's in your cell phone. It's in the smart thermostats. It's in your microwave oven. It's in your TV set. These sorts of things don't need to be doing a bazillion transactions.
How many such devices is it in?
It's hard to count because it is open, because it's public domain. A lot of people don't tell us. So until a few minutes ago, I did not know that SQLite was flying on the space station.
You missed the intro.
Oh, sorry.
You missed the intro. So
50 million AOL installation CDs.
So yeah, AOL was an early adopter. Do you remember back in the early part of this millennium where you get the AOL install CDs, $10 a month or something? Do you remember those?
I never was AOL.
SQLite was always on those.
Very few people were, but they still got the CDs.
So, but SQLite is also good as an application file format. If you're doing a traditional desktop application of some sort, and instead of doing file save and writing out a bunch of XML, make it a database. You get all this powerful query language and transactions. It's great for what I call the lingua franca of a federation of programs. You got a bunch of graduate students working on a problem, and you're writing in Python, and you over here, you're doing C++, and you're doing Ruby, and this guy over here is doing PHP. Oh, you're doing Lisp. All these guys are doing different programs because that's what they want to do, but they all got to talk to each other. Why not use an SQLite database file as your means of your common mode of communication? It's often used as a local cache for an enterprise database. So you're on a device, you want to download data that's relevant to the device so that the device can continue to operate while you're off network. You're on your phone and you're going through a tunnel and you've lost reception. You're off network for a while. and it works well. It's also good as an interchange format. So, for example, you know the program guide on your cable TV, and it comes down to the set-top box. In a lot of cases, it's being beambound from the satellite to your set-top box as an SQLite database. And then, you know, and then the window that shows you what that's just an archery query. So here's your decision checklist about when to use or what data storage engine to use for your project. Is the data remote? If the data is on a different device from the one that your application is running on, use one of the traditional client-server databases. If it's big data, if it's more data than you're comfortable putting in a single file, use one of the traditional client-server databases. If you've got concurrent writers, if you're trying to do a gazillion transactions per second, use a client-server database. That's what they're for. And these are all very important problems, and these client-server databases are all very good at solving them. But there's a lot of problems that don't fit any of those categories, and for all those other cases, just use SQLite. And where people mess this up is that they do the first part of that checklist right, and they get down to the bottom and say, oh, well, I don't have any of these problems. I'm just going to open a file and write a bunch of JSON into it, or some binary format that I made up. And this happens a lot. And that's the use case for SQLite. SQLite is not really competing against these other database engines that you study all the time. It's competing with fopen. That's its goal. So SQLite is found in lots of different things. As Andy was saying, it's in all the phones. It's in your Mac. It's in your Windows 10 machine. It's in the web browser. It's in lots of applications. It's built into a lot of programming languages. And it's just appearing in devices all over. We're pretty sure, we can't measure this because it is public domain, but we're pretty sure it is the most widely used database engine in the world. I think that it is probably the #2 most used piece of software in the world. I'm thinking that #1 is the zlib compression library. There's probably more deployments than SQLite, but other than that, I'm not aware of anything that does more. Okay, I've got one marketing slide, actually two. This is the first of two marketing. I've got this question in the back.
Yeah. What percentage of the code base deals with the SQL part of SQLite?
I've got a slide coming up, so hold the question. Okay, so this is I've got two marketing slides. I just want to point you, this is a graph of Apple's stock price from when they originally went public in 1981 up until about 2012. And from there, it's gone on up. This is before the split. They had an 8-to-1 split, but adjusted for the split, it would be now at about 1,000. And you can notice how the stock stayed around $10 or $15 per share for over 20 years. And then it suddenly started this rise up to 1,000. Okay, absolutely true. SQLite was introduced onto the Mac platform there. Okay, I'm just saying. I'm just saying.
But did you buy a bunch of Apple stock then?
Unfortunately, no. What I'm going to talk about here is I'm going to go over how SQLite is implemented, because you're all database people, I assume, and even if you're working on one of these systems that does a gazillion transactions per second, and SQLite is really not what you're into, it's an important database, and you need to understand it. And so I'm going to give you an overview of the implementation so that you understand what it's doing, and so that if you want to go and look at the code, you've got kind of a roadmap. The code is available online. Here's how you get it. There's two places that you can get it, and it's readable code. We put a lot of comments in the code, and the readable comments, we see tweets about how, oh, you should read SQLite code. It's really easy. So you can actually study this. My goal is to give you a roadmap so that when you just pull a random bit of code out, you have some inkling of what it's trying to do. So any database engine, I like to think of them in terms of a compiler and a virtual machine. So you've got SQL that comes in, and you've got a part of the program that's going to compile, you've got part of the database engine that's going to compile the SQL into a prepared statement. This is, I think of every statement of SQL as a miniature program. And the prepared statement is the executable. And so this is like GCC. And then you get a prepared statement, and then you run the prepared statement. That's like just executing the binary. That's the way we like to think of it. This is the stack of SQLite. There's a parser, a code generator, virtual machine, B-tree layer, pager, and an OS interface. I'm going to talk about each of these in turn. At the top, there's a parser. It's a standard kind of parser. We did the tokenizer is written by hand. It's only a couple hundred lines of code. You know, when you're studying compiler construction, you have these big chapters about Lex and lectures and stuff, and they use all. I've never understood that because it is so easy to write a tokenizer in a couple hundred lines of C code that is at least 2 orders of magnitude faster than anything Flex will ever generate. So I don't know why they do that, but
I've never heard anybody writing their own parser by hand. That's crazy.
No,
Okay.
this is just the tokenizer. This is just splitting it up into tokens. Now, the parser is a traditional LALR1 parser. It doesn't use YAC. I wrote my own parser generator when I was a graduate student. Okay, and it has the advantage over YAC that it generates a parser that is reentrant and thread safe. And back when I was doing this, Bison and YAC parsers were neither of these things. They may have fixed that now. I don't know. I haven't kept up with it. So, but it's a traditional parser. These are the files where you can find this stuff if you want to look at the code. The source code to the lemon parser generator is included in the source tree, and documentation is included in the source tree, so you can learn about lemon. And then the structures that define the abstract syntax tree are in that header file, and the tokenizers in that file up there. So moving on down further, we have the code generator, which does semantic analysis of the parsed code, transforms the parse tree in ways to try to make things more efficient, does query planning, and then generates bytecode. The output of this is the prepared statement. So these two things implement the compiler. Think of these two steps as GCC. They take raw program text and turn it into something the machine can understand. And of course, the rest of the stack is going to be implementing the machine. So the virtual machine in SQLite it's a bytecode interpreter. A lot of other database engines, they will they just walk the parse tree, and that's how they execute. But I wanted to do a bytecode interpreter. The original bytecode interpreter was a stack base where you push things onto a stack and then operate on the stack, just like JVM and all the others. It seems like every virtual machine always starts as a stack-based machine. But we changed it to a 3-address machine because that actually turns out to be more efficient and much easier to write optimal code for. So it's really simple. It's a big for loop. Program counter equals 0, program counter plus plus, and inside the for loop there's a switch, and it switches on the opcode, and there's a case for every opcode. And as part of the virtual machine, I also include the implementation of the built-in SQL functions. So they're included there. Talk more about that later. So here's an example of what the bytecode looks like. I won't walk you through this, but you can look at the bytecode for any SQL statement that SQLite can generate by just putting explain up front, like this. And the documentation for the opcodes is available online if you want to try and decode that. This is doing a full table scan, so this one's pretty simple and I could fit on one slide. For a join with subqueries and lots of conditions, this might go on for hundreds or even thousands of instructions. But a simple table scan, pretty quick. If you want to study this and you want to look at what the bytecode SQLite generates is, let me tell you how to do that. You need to do a custom build. And so to get the tarball, get the source code, do configure, and I like to do disabled shared because autoconf, if you don't do that, it does all this freaky shell script stuff to do shared libraries. And you can do that if you want to, it'll work, but I find it confusing, so I always disable it. And before you do make, there's an extra C preprocessor defined that you need to give it. And that's going to add these comments. I'm going to go back a slide. Over here on the far right, we've got comments that help explain what each opcode is doing. And by default, those are not generated because they take up space, and it takes CPU cycles to generate them. So in a production environment, we don't want to do that. But if you're debugging, they're very useful to help you quickly see what's going on. And so you'll probably want to include those. So once you get that thing compiled, what you've compiled then is a command line shell. It's just a simple program that reads SQL statements and then sends them to SQLite to be executed. And this command line shell, SQLite 3, if you give it a line that starts with a dot, a period, that's special. The shell doesn't send that to SQLite. It does some special processing. And the dot explain sets up the output formatting so that you have nice, neat columns, and it automatically indents loops so that you can spot the loops more easily. And so that's a nice thing you want to do. So you want to be sure and type that. And then you just type in explain and then the rest of your query, and you'll get to see the bytecode. So moving on down the stack, this is kind of the boundary between to the storage engine. And a lot of places I go and I talk to people about databases, and when I say databases, to them, the storage engine is the database. This is their focus. How can I get as many writes to disk as possible? My view is a little different. I think that this whole stack is the database, and the bottom part is just the storage engine. And if you've got just a key value pair type thing, you only have half a database. That's my opinion. Really, in my view, the interesting stuff is happening up above. All the query planning and the analysis of the declarative programming language, that's where the interesting parts are. The bottom is just a storage engine. Now, there is a reasonably clean interface for this in SQLite. And what a lot of people have done, including some people who will be speaking to you in this lecture series, is they have taken the default SQLite storage engine out, just stripped it out, and plugged in their own. So then they've got an SQL system on top, and then they put their own whiz-bang storage system underneath. Because as you'll see in a minute, my storage engine is not like cool and has the latest algorithms. It's old tech. It's old school. So the B tree layer, we support B trees and B plus trees. There are multiple B trees per disk file. One B tree for each table, one B tree for each index. Variable length records. Uses a very efficient coding mechanism. It's accessed via cursor. So when you're working with B trees, you open a cursor into a B tree, and then you can seek the cursor and advance the cursor backwards and forwards. And it allows for multiple cursors to be open on the same B tree at the same time, and including cursors that are changing the B tree, and it takes care automatically of that people don't write things out from underneath each other. I'm going to go back over. This is just I don't know if I made clear. This is just sort of the 30,000 foot view. I'm going to go back over all of this in more depth after I finish the quick overview. Next on down is the pager layer. And this is the part that implements your transactions, your atomic commit and your rollback. The pager views a database as a bunch of pages. They're numbered starting with 1 because page 0 is like our null pointer. And the page size is a power of 2 between 512 and 64K. The pager has no idea what the content of the page is. It doesn't care. It's just managing the pages, handing them to the B tree, and then dealing with transactions. It also provides concurrency control because with SQLite you can have multiple processes talking to the same database file at the same time. And there's not a server controlling this. They're all peers. And so there's got to be a mechanism to make sure they don't step on each other. And that's handled by the pager layer. And then at the bottom, we have the operating system interface. This is the portability layer. This is how we allow SQLite to operate on Windows, on Mac, on various embedded database or various embedded operating systems, including some custom operating systems. You can plug in new OS interfaces at runtime, which is an interesting feature, which I'll talk about in the next slide. And I say an OS interface. People have substituted. We have an example of this. An OS interface that talks directly to hardware. It bypasses the operating system completely. So you can actually buy commercial off-the-shelf devices, little gadgets that are using SQLite, and they plugged in their own OS interface that talks directly to the flash controller, and they use SQLite as their file system. They have no file system on the device, they only have the database. Interesting concept. Now, because it's runtime pluggable, we have this concept of a shim, where you can plug in your own OS interface that doesn't really do a complete OS interface. It just maybe changes the calls around a little bit and then passes it on down to the real OS interface. And this could do things like you could add encryption or compression. You could do logging. We use this a lot for testing because we can plug in a shim that can simulate hardware failures. And that we can prove that SQLite is going to be able to recover gracefully from a hardware failure. And there's some examples, implementations of this sort of thing if you want to play around with it. So there was a question in the back on what the percentage was. Here is the graph. Here is the chart. The parser is the little green. This is source code. If you looked at compiled binary, the ratios are going to be a little bit different, but this is roughly the same. And in particular, the parser is going to grow a little bit because the LALR1 language is a very compact notation. But not a whole lot. And then the code generator is the bulk of it. Code generator and the virtual machine and the parser together are over half of it. The B tree layer is this thin little slice right here. It's really not that much. So that is the 30,000 foot view of SQLite. Now, what I'm going to do now, my plan is to go back through this whole thing again, but this time from the bottom up and get into a little bit more detail about how things work so that you better understand what SQLite is doing behind the scenes. So let's start with the pager. Again, this is what handles power-safe transactions and currency control. This is the thing that makes sure that you can roll back your transactions, or that if you crash in the middle of a transaction, your database is consistent, that transactions are atomic across power failures. It also handles currency control and provides an in-memory cache for the disk controller. So when you start out, you're getting ready to read the database. Here's a little diagram I've got. I guess it's labeled disk. Now it means NAND flash, right? Because I don't think I even own a computer that has spinning Rust anymore. They're all, but you know what I mean. So all the data is on disk. There's an OS cache, an operating system cache, but it's empty right now. There's no content there. The cache is cold. And you want to read from the database, and so the first thing you have to do is get a shared lock, and that's drawn on in RAM because you think about these locks, they don't really persist. If the system crashes, all the locks go away. So you get a shared lock, and that prevents other processes from changing the data out from under you while you're trying to read it. And then you read a few pages that you need in order to do your work. And everybody's happy. Now suppose you want to make some changes. You want to change the database. You want to write. You want to insert some data. The first thing it does is it gets a reserved lock on the database file, which says, you know what, I'm getting ready to write. We can only have one writer at a time. I call dibs. It's not writing yet. Other people can continue to read, but this guy has dibs. He's claiming the right to the reservation to make a write. And once he does that, then he stores the original unchanged content of the database files database pages he's going to change in a rollback journal. And this is a file in the same directory as the original database, but with the name -journal appended. It's a rollback journal. This should be familiar to all of you. I'm just giving you details. And then, after he's done that, he's free to make changes to the individual pages in user space. Nobody else can see this yet. Other processes continue to read the old original data. Now we're ready to commit. So the first thing we have to do is fsync or flush the rollback journal to disk. This is important because if you lose power, that stuff's got to be there in order to recover. Sometimes people don't care about recovering after a power failure, in which case you can turn that step off. And you know what? To a first approximation, this step of forcing it out to disk is what takes all of the time. Everything else is free. This is what costs time. So you can turn that off and it'll make the things run a whole lot faster many times faster. But if you lose power and the writes to hardware occurred out of order, it could corrupt your database. So anyway, it flushes it out to memory. Then it gets an exclusive lock on the database file, which prevents anybody from being able to read the database file, because we're getting ready to write on the database, and we can't write to it while somebody else is reading, because that would read it out from underneath them. So then we do the write system calls, and then we have to flush that out to disk with another fsync. And then the moment of commit, we delete the rollback journal. Or maybe we truncate it or set it to 0. Or somehow we make the rollback journal unusable. And that's what causes the commit to occur. Before this point, if we lose power, the rollback journal is always sitting there. So here we've lost power. And in the middle of writing to the database file, we didn't get the complete write done. We've lost power. And now power's been restored, and we're coming back up, and somebody gets ready to read. And they get the shared lock, and they immediately notice, oh, we've got a hot journal over here. It's a journal that didn't get processed correctly. So it immediately goes to an exclusive lock and rolls the whole thing back, restoring the database to its original condition. So this will always happen until you delete the rollback journal. So the delete is when the transaction commits. That's rollback mode. That's the default. That's the most reliable. But it's kind of slow. You can have multiple readers or one writer, but you can't have a reader and a writer going at the same time. So we have another way of doing this called write-ahead log mode. This is not the default, and I'll explain why this is not the default in a second. But with the write-ahead log mode, it starts out the same. You get a shared lock on the database file. You read it into user space. But you go ahead, it's okay to go ahead and make changes in user space right away. You don't have to log the old original content. And you don't have to upgrade your lock from shared. Other people can continue to read. And then when you want to commit, you just write the changes out to a write-ahead log, which is the name of the database file with -wall appended. And you're done. You didn't have to fsync. You're finished. Now, this is not durable. I'll get to that. But it is atomic. And I've got a little dot here in the last record. Of course, all of these pages have a header which says which page number it is, and there's a checksum and some other things. And one of them is marked, oh, this is the last record of the commit. So now I know the transaction's finished. So that's great. And then another process can come along, and it wants to read too, and it's reading some of the pages, some fresh pages off the database that the other guy didn't touch. But it also wants to read one of the pages that the first user has changed. And it has to read that change out of the write-ahead log. You see? So this page came out of the write-ahead log so that it reflects the change, whereas these others were unchanged and it read them directly from the database file. So you can see that we can have some readers that were reading completely out of the database. They're looking at a snapshot in history, whereas this guy's looking at what the current version is. And then this guy might want to make some changes, and then he just appends to the log as well. And so you can have multiple readers going at the same time, looking at reading from different points of the write-ahead log and the database file, and have snapshot isolation. The reason that we don't do this by default is that when you're trying to get a page, you have to know if that page is first in the write-ahead log before you read it from the database. And the way we do that is that we have a little hash table that's in shared memory. But if the hash table is in shared memory and you have multiple processes trying to access the database and it's on a network file system and on their different computers, that's not going to work. And so for the other scheme works fine if you've got processes on separate computers accessing it over a network process. This one does not. It also does not work on some operating systems that have dodgy memory mapping, because we use memory mapping for the shared memory. So,
Which ones?
not on tape. It's the ones that you've heard of, actually.
Sure.
They claim to have fixed it. We reported the bugs, and I think they may have fixed it, but whatever. So this is an option. A lot of people use it, and if you're using Firefox, if you're using an iPhone, if you're using Android, they normally enable this because this works a lot better. But it's just an option. Oh, wait, but this wall file can grow without bound. At some point, you've got to get this data back into the original database file. So we have a checkpoint operation that runs automatically, or you can set up a separate thread or a separate process to run checkpoints. But if you don't do that, it'll do it automatically when the wall file gets big enough. And to do a checkpoint, the first thing we have to do is make sure the wall gets persisted to disk. This gives you durability. And you can also set it up so that it automatically does this fsync after every transaction if durability is important to you. Turns out most applications, if you lose power and you lose, if you lost power and when you come back up, if you miss the last 3 transactions, most people don't care. They'd rather have the performance. But if you really have to have the durability, you can set it up that it flushes the disk after every transaction. So then periodically, we will take the content of the wall file, roll it back onto the disk, and that is, and then we truncate the wall file and start over. And that's a checkpoint operation. Question in the back of the room.
Yes. Even in the situation you described, where multiple computers reading over NFS or something like that, how do you do locking then? You have to make sure you have sync the lock to disk.
The question is, how do we handle multiple computers reading the same database file over like NFS? Yeah, whatever your network file system has to support POSIX advisory locking or the Windows equivalent. And if it doesn't, and a lot of them don't, you run the risk of some corruption.
The lock is not something you roll yourself, put into the database file.
The locking is POSIX advisory locking. Actually, we have multiple. We got the pluggable OS layer. There's a different OS layer that will substitute creating dot files in place of POSIX advisory locking for cases where. But that's a lot heavier, slower, and if you crash in the middle, the lock doesn't automatically go away, so you've got to go back and clean it up. So either way, I'm running behind. I'm running badly behind. So I'm going to go faster. So that's kind of the discussion of the pager. We didn't talk about nested transactions, pluggable page cache, or how we test this thing for crashes. How do you know that this really works? How do you know that this is really going to recover on a power failure? That's an interesting problem. I haven't talked about it. The B3 layer is next. Multiple. Yeah.
Question about the granularity. So it's not like all the transactions are in units that are the full page size.
Yes.
Is that a problem for any of your users that they say, oh, I'm only changing a little word on
So the question is, when we're logging in either the rollback journal or in the write-ahead log, we're logging complete pages rather than just the change. And I know that there's some other, like Berkeley DB just does the change. And we benchmarked it. It's not a big performance hit, and it sure makes things a whole lot simpler and more reliable if you've got the complete page there rather than just the change. So, the Berkeley DB people will be here in a few weeks, and you can ask them. They might have a different opinion of this. I don't know. Okay. So in the B-tree layer, there's multiple B-trees per file. We use B+ trees for tables with a 64-bit integer key, and regular B trees for indexes. A table looks like this. It's a key with arbitrary data. The format of the data, the B tree doesn't know what that data is. It's just binary to it. The format is actually interpreted by the next layer up. And of course, you've got a root page, and it points to child pages. By pointer, I mean it's just a page number. It's a 32-bit page number. And all the data, and it's a B+ tree, so all the data is in the leaves of the tree. The keys can appear more than once in a B+ tree, but because they're small integers, it's not a problem. Because our B tree is used for the tables, it's optimized for appending rather than for arbitrary inserts. Oh, I did want to point out, amazing fan out. Because I'm only showing a fan out of 3 in this simple diagram, but you really get fan out on the order of 1,000. So it really works best. We use variable length integers, and this is the variable length integer encoding where it reads bytes that have 0 in the high order bit and uses the 7 lower bits, or it uses the entire 9th byte in order to construct your integers. And this was a mistake. And I give you this is a failure. So if you're ever doing something like this and you need variable length integers, don't do them this way. Instead, do them like this, where the first byte tells you, the magnitude of the integer somehow or another. So here's an example where if the first byte's less 240 or less, then that's just the value. If it's between 241 and 248, there's some little formula that gives you larger values, and so forth. If the first byte is 255, then it just takes the next 8 bytes, and that's your value. And the reason for doing it this way is when the first byte determines the size of the variable length integer, which is very important for efficiency in parsing this. And the other thing is that you can actually compare two integers using memcompare without having to decode them. Okay? So this was a mistake. Always do it. The way I did it was a mistake. Always do it this way. The other thing I wanted to point out is how the pages are laid out. There's a header on each page, and then I have a section in here which are 2-byte offsets to each row within that page. And then down over here I have all the rows. I did this backwards as well. If you ever are doing a B tree, let me suggest that you flip it around the other way. Put the header at the end and the pointers to the offset before that, and then the content here. And the reason for this is you've got variable length rows in here. And if you're having to parse this stuff out, and you could potentially have been handed a corrupt database file, because remember, SQLite is used to pass information around on sticks and stuff. Somebody could have deliberately given you a corrupt database file in attempting to crash your system. So when we're parsing this and we're doing these variable length fields, we don't want to do a buffer overrun. And the way I've got it now, because the content area goes all the way to the end of the page, I have to be very, very precise in making sure I don't overrun the buffer. Whereas if I had done it the other way around and put this header and this other stuff at the beginning, I've got kind of an overrun area, so a little bit of slop, and you could save a lot of performance that way. Just some hints. Okay.
So it's not so much for performance; it's for safety.
Right. The question. It's for performance in an environment where we want to guarantee safety. Because SQLite right now has to spend a lot of CPU cycles making sure that we never overrun that buffer, when in fact, in practice, you never do, unless somebody's trying to break into your program. So those are essentially wasted cycles. Okay, so indexes are stored as regular B trees, and we treat an index as just the key. There's no data on an index. It's just a key. And it's binary data. The B tree doesn't know how to sort these things because it's binary, but the next layer up hands it a pointer, a comparison function that allows it to sort these. And we'll talk about it in a minute. B trees, the data is distributed throughout the tree, or the keys are distributed throughout the key. The key is the data, but the keys are not duplicated. Remember, in a B plus tree, the keys are duplicated. Here, it's not duplicated. There's only one key, one instance of the key in the table for each one, which is important because now the keys are much larger. But you have reduced fan out, so searching takes longer because the keys are larger, fewer of them fit on one page, it doesn't fan out as fast. Search takes a little bit longer. We've got SQLite set up so that there's always a minimum of 4 keys on every page. So I'm going to skip that slide in the interest of time. Now we've got a bunch of B trees in the same file, and these individual pages can be interleaved all through the file. And the only thing that you need to know is what the root page of each B tree is. If you want to see where the pages are, you can download the source code, do configure, do make showdb. Showdb is a little utility that we wrote that kind of decodes the file format. And they do showdb database page index, and it will actually show you what each page of the database file is used for. And we can see here that the first page is both a root and a leaf. So that particular table fit on a single page, and it would all fit there. And you can see a bunch of other tables. Down here at the bottom, I want to point out we've got overflow pages. Because I mentioned earlier that SQLite handles up to 1 gigabyte of content in a row, but the pages are like 1K. How do we do that? Well, if it doesn't fit on one page, it puts a little bit on the original page and then puts a pointer to an overflow chain. And this is just a linked list. And when I was designing SQLite, I looked around at all the SQL databases I could find, and I didn't find any that really had large blobs or strings. And so I thought, you know, I'm going to support this, but it's rarely used. It doesn't have to be efficient. I didn't try to make this fast. But amazingly enough, it turns out to work very well, even for megabyte size strings and blobs. Adobe discovered this for us. And the Lightroom, the Adobe Lightroom product, they have to store a lot of thumbnails of images, and they use SQLite as their application file format. And they're wondering, do I store thumbnails directly in the database, or do I just store the file name and then write the image out to a separate file? And they ran it, and it turns out for blobs less than about 50 or 100K, it's actually faster to write it into the database than it is to write it to the file system. I believe this is because if you write it to the file system, you have to open and close. And it's the overhead of the open and close system calls that slows you down, whereas the database file is continuously open. So we're faster with that. All right, the B tree primitives, again, you access the B trees by cursor. You open a cursor. You seek on the cursor, forward and back, ask for the data or the key. Close the cursor. How do we find out where the root pages are for each of the B trees in the file? So there's a special table in every SQLite database called the SQLite master table, and the schema looks like this. It's there by default. You can't change it. And it has the type, which is table, index, view, or trigger, the name of the thing, the SQL that originally created, the original SQL text, and it also has the root page. So, and this particular table always has a root at page 1. So we can go to page 1, where there's a B tree there, which is this thing. We can read this B tree and find the root page of every other table in the file. And here's just an example of how you can actually see that table in action.
Does this mean if you clobber the root page, the first page in your file, you just lose everything?
Right. So this means that if the first page gets clobbered, it's going to be really hard to recover much from that database. Yes, because you've lost the schema. Yeah. The schema is stored on the first page, or of course, in overflow pages as well. So that's the B tree. We didn't talk about free list management, auto vacuuming, shared cache. I'm looking at this clock here, and I'm running way over, so I'm just going to slip through this. The virtual machine is it defines the format of the records, and I'm going to very quickly go over this. The records, SQLite has this interesting property that is that it kind of ignores column types. You can put anything you want in any column. You don't even have to have a declared type on column. SQLite derives from the scripting language community, from Tickle. Anybody heard of the Tickle programming language? You used it? SQLite is, in fact, a Tickle extension that escaped into the wild. This is the truth. So, kind of a typeless Python type thing. So we have to store the data type for everything, and so we've got a bunch of variable length integers that define the data type, and then we have the actual data. And so here's how the integers decode. Like an integer of 0 means that it's a null. An integer 6 means an 8-byte signed integer. And then for strings and blobs, it's these values here, and you've got a little formula that gives you the length. So most of the time, these type codes are a single byte. Here's an example in coding. Create table ABC. Notice I didn't put any type information in there. I just 3 columns ABC. And you can do that in SQLite. And I'm inserting 177, a null, and hello. And so here's the header in these 4 bytes. And then here's the 2-byte integer for 177. And the null doesn't take up any data at all. And then there's the string hello. So that's the encoding. The code generator, it's in these files. In the interest of time, I'm going to skip over this really quick. If you're going to work with the code generator, I suggest you enhance your shell by downloading the tarball, doing configure, and then adding these extra sharp defines to the make file, and then doing the build. And now you get some extra command line tools that allow you to, for example, print out a parse tree in kind of ASCII art. The clock is just spinning around so fast, so I'm going to slip right over this, and you can go and read this at your leisure if you want to do this. But we've got really cool tools that if you're in the debugger and you're single stepping and you want to look at a parse tree, you can actually call some routines and it'll print them out for you. You've also got lots of extra pragmas that allow you to trace. It prints out each virtual machine opcode as it runs it. So I want to get on into how the query actually runs. So here's an example of how the data is stored in SQLite. You've got the row ID and then all the data for a simple little table here. And if you want to query this table, give me the price for peaches. Of course, one way to do that would be to seek to the beginning of the table, step through each row, pull out the fruit field, see if it's equal to peach, and if it is, output the price. It's a full table scan. That always works. And of course, but if there were like 7 million rows, that would be really slow. So, well, you could also ask for it by row ID, and then it'll do a binary search, and that's very fast. But if you're running a grocer, you don't want to have to remember that the secret code for peach is 4. That's crazy. You really want to ask for peach. So for that, we have an index, and the way an index works is it just it creates this key over here that contains the value being indexed and the row ID. And because the row ID is unique, this guarantees that each row in the index will also be unique. So, and in cases where the actual fruit is not unique, the row ID will disambiguate it. And so once you have that to query for the peach, you can do a binary search for the entry that has peach. You read off the row ID, use that to do a binary search in the original table that gives you the whole record, and then you can pull out the price. And that's great. And if you could do the same thing for orange, and it goes to the first entry with orange, gets the row ID and gets it, second entry, and gets that one as well. And this is just by stepping through the B tree. But if I said orange in California, it'd have to do orange. It gets one. Then after it does the lookup for row 1, it has to check to see, well, is it in the state of California? No, it's in Florida. I have to reject that row. I did that B tree search, that binary search for not, and we hate that. That's extra work. We would like to avoid that. And so you think, well, maybe I'll do an index on state, but that doesn't really help either, because then you could look for California, but then it'd have to check for grape, and then you'd miss one there too. It's the same amount of work. So what you need there is a 2-column index where you have both the fruit and the state in the index. And where the fruit's a tie, the state breaks the tie. And it's the same type of thing, but now you can look for orange and California, get the 23, and immediately look it up. And that's a lot faster. That's a lot better way to do that sort of thing. You could do even better than this, though, if you built an index that contains all the columns in there. The fruit, the state, and the price. And then when you do select price from table where fruit is orange, you could do a binary search to find the first entry where it says orange California, and the price is already there in the index. And you just read it straight out of the index. You don't even have to look at the original table. This is called a covering index. If it's an OR, of course you can always do a full table scan. Just start at the beginning of the table, read column by row by row, checking the condition and the where clause to see if it's true, and then outputting the price. But we'd really like to use an index, and in this case, it will take 2 separate indexes, one for fruit, one for state, do the lookup for the row IDs, take the union of those, and then pull the prices out that way. Another thing it can do, if you've got a 2-column index on state and fruit, but you want to look up by fruit, you think, well, I can't really do this because I can't do a binary search for the second field of an index. But SQLite will do this, and the way it does that is that it recognizes there are not many states. There's just not many values. So it will iterate through all the possible values for state, and then within each state, look for the fruit orange. We call this, there's no official name to it for this as far as I'm aware. We call it skip scan, but it will try and do this if it knows that there aren't many distinct values, or just a few distinct values for the first column. So we can sort. Always do a sort. A sort is the most expensive thing you can probably do in a database engine. If you give an order by clause in SQLite and it knows that it's going to come out in the right order anyway, it just throws the order by clause away. It doesn't force you to sort. So be generous with your order by clauses. If you give an order by fruit and you've got an index on fruit, it will walk the index and then do pull out the row IDs and then do the search and pull out the rows in the correct order. And you think, well, that's still in log n. I haven't saved anything. Well, actually, you have, because it uses a lot less memory. And also, if you're looping through this and you get only a couple entries through and you say, okay, I'm going to quit, it didn't have to do all those other lookups before it did the search. So this is a much more efficient way of doing it in practice. And of course, if you have a covering index, it just spins right down the covering index. If you have a covering index that's almost there but not quite, here we want to sort by fruit and price, but we've got this pesky state row in the middle, which kind of messes up our sort order. It will read down as much as it can. It'll read all the unique values for fruit and then gather them and sort them separately. So it does lots of little sorts, which is more efficient because it can start outputting rows immediately before it scans the whole table, and the sorts are smaller. If you've got something like a union with 2 order bodies, it will actually break this up into 2 separate queries, run them as coroutines, and then take the union of the output.
So basically, you are fully inverting the database with all these indexes.
Yes.
Who decides, are you doing it blindly for all of these potential choices, or there is some decision making?
Right, you're the application programmer.
Embedded, so this requires a lot of memory, a lot of maintenance. With simple updates now, it's not only just worrying about the write ahead.
Well, I mean, the indices are maintained automatically. You, the programmer, I'm skipping over some slides here because we are out of time. You, the programmer, have to come up with the indices. SQLite is not going to do that itself. But this is the key advantage of having a query language. And this is an important slide. It's probably the last one I have. Because if you've got a query language like this, you can code, you can design your application, you can build it, you can spend weeks coding it up. You get down to the end, and you've got a performance problem. Oftentimes, you can fix that performance problem just by doing create index. And suddenly, you've got completely different algorithms that are being used. And you can do this the night before you release your product. Whereas if you're using a key value store or something else that doesn't have a query language like this, and you get down to the end and it's not working, it's not performing well, then you've got to spend some serious time recoding. You can't do that on the day before you release. You've got to recode and retest. That's the beauty. That's why it's so important. That's what this top half, the part above the storage engine, is so important, because it gives you that flexibility.
I saw that you have all these explain utilities, debugging utilities. Do you combine those in order to help you to identify bottlenecks and do the tuning with the indexing?
So the question is, do I provide utilities to help programmers identify bottlenecks and do the tuning?
That's right.
No, that is a frequent request. It's on our to-do list. I mean, there are things there. We provide mechanism, but it's not an especially intuitive thing to do. You have to kind of know what you're doing. But we need an automatic tool that looks at the schema, looks at your query, and say, hey, you should consider this index. We don't have that yet. That's on the to-do list. So, code generator, we didn't talk about join order selection. I also skipped some slides. There's a lot of other cool things in here. The query planner stability guarantee. This is an important part of an embedded database, is that there's all these different algorithms that it can choose, but in a commercial database, in a data center, you want it to adjust its algorithms as the data changes to select the best algorithm for the current state of the data. If you're doing an embedded product and you're shipping millions of these things, you don't want the query planner changing its mind for some small percentage of the users out in the field, because usually it will do a good job, but sometimes it might choose a bad plan, and then you're going to get bug reports. You want the query planner to always do the same thing, and SQLite can be set up, in fact, in its default situation, it's always going to choose the same query plan for a given schema. And it won't change that unless you run analyze or change the schema around.
And that's because it's a heuristic-based system.
No, it's actually a cost-based system, but the costs are fixed. They don't automatically recompute.
Do you maintain statistics?
When you run analyze, the analyze command.
Okay.
So if you rerun analyze, it's going to get different statistics, and then it might choose different plans.
Sure.
So don't do that if you're concerned about query plans changing out from under you. Okay, other topics. I haven't talked about virtual tables. I haven't talked about the full text search engine. And this is a really cool thing because it actually implements LSM trees on top of B+ trees. And that's a really cool idea. And it's actually very efficient. It's faster than Lucene. R trees, memory management, how we test this thing. We got a really impressive test suite, and that's very important to us. That is, I'm slightly over time, and I'm happy to talk about any of this. This is the slightly low. We've gone to a slightly lower orbit, and I've given you sort of an overview of how the system works. There's a lot of details here. Love to hear your questions and your feedback, and you can also go to the mailing list and visit us there. Thank you very much for your attention. I'm sorry for running 5 minutes over. If people have to leave, you're welcome to step away. Otherwise, if there are questions, I'll be happy to take them now.
Thank you, Richard. I will try to do 2 questions.
Yes, ma'am.
So the way I see it is there is a trade-off between how minimal or how lightweight you want to be, and what is the flexibility with the query language you provide. And do you think that you have reached the optimal point? So with variables or Internet of Things, there is a possibility that you can actually.
All right, so if I understand the question, you're asking, yeah, there's trade-offs in any system because on a full-scale data center-oriented database, you've got a lot more power and it's doing lots of fancy things, and we don't do that. And we do, and so the trade-off is because we're using less power and it's easier to maintain, and we want it consistent across millions of devices. Have we found that right balance? Well, we're constantly adjusting that balance. We take a lot of input from people who are actually using this stuff, and we try and adjust it. I talked about the query planner stability guarantee and how it doesn't recompute plans based on evolving data. There's a compile time option that will make it do that. And so if you have a very specific need where you want it to violate that guarantee but work more like a mainframe database, you can make it do that. And so we provide a lot of options that way. Have we found the best blend? I think so, because there used to be a lot of these embedded SQL databases, and now there's just SQLite and maybe SQL Anywhere, and the rest of them have kind of gone away. So and
the Java ones too.
Oh yeah, the Java ones. Does anybody ever use those really?
Get one thing on tape.
Yeah. Yeah, I think the market seems to be saying that we're doing well. Maybe we're just lucky. I don't know, but I think but you're right. There's a balance here. You got to find the right mixture of features and capabilities, and I think we've got a niche, and we're trying to do that. Yes, sir.
SQLite is known for its amazing testing philosophy. How did it improve over time?
Okay, so the comment was SQLite is known for its testing philosophy, and the way this came about was a couple of things. One, I was doing some work with some avionics companies who wanted to put SQLite into safety critical systems, and that made me aware of this spec called a DO-178B. DO-178B, and that's a design spec that the FAA uses for validating software that's in safety critical functions in aircraft. And it made me aware of it. I learned about it. That took a lot of time. And then also, when SQLite started to go out in a lot of phones, we started to get back a lot of bug reports. It's you think you write really good, solid code, but it's amazing if you put your code out on 1 billion devices, how many bugs will come up. It will truly amaze you. And so we spent about an intensive year kind of converting all of our processes over to this DO-178B style of work. And we made this test suite, which is now, it's a proprietary test suite, and that's sort of our intellectual property. That's the company's intellectual property. The code is public. The test suite is our IP. That's our company's value. And we've got this massive test suite that does 100% MCDC, modified condition decision coverage of the entire thing. And it's been a huge, huge benefit. Since we put that in place, bugs do come up, but they're infrequent. We really haven't had many bugs. And it also gives us enormous flexibility to change things. I had this conversation with the Postgres people. because they've also had a very reliable database engine, and asked them, how is it that you're so reliable, and you don't have this this big test fleet like we do, because we depend on that. And what we really decided was they keep their reliability by not changing anything. The code works, leave it alone. Whereas we have now the flexibility to rip out entire subsystems and completely recode them on a point release, and we do this fearlessly. So it takes a lot of work. I spend more time writing test cases and debugging test cases than I actually spend writing code. But in the long run, it saves you work, because we just don't have a lot of bugs to fix. And so it's worked out really well. When I was a graduate student, when I was your age, I thought, oh, I don't need all this process. It's just paperwork. This is nonsense. But what I've come to realize is that it actually does work. It really does help you. Any other questions? Yes, sir.
Keep it quick. Sorry.
Yeah, and I guess people can find me around. I'm here the rest of the day, right? And you can find me. And
You have a quick question, like.
Yeah, I started writing SQLite for non-volatile memory.
Is there a special version of the SQLite for non-volatile memory? No. I mean, you could plug in your own little OS layer down at the bottom that somehow is special for non-volatile memory. And remember, some people, well, no, you're thinking. I was thinking in NAND flash. No, you're talking about this thing where it's in memory all the time, and the memory's operating at full speed. It just doesn't forget when you lose power.
PCM, patient
Yeah,
memory registers.
right, exactly. It works at full speed. NOR flash was the old technology, yeah. No, we haven't really looked into that. It's not really optimized for that. It's old school. I guess we could.
All right, let's thank Dr. Hipp again.
Thank you for having me. Thank you.
So there's not a database talk next week. I think in October.